Hello there! Today we're going to be looking at the problem Equalize list. Problem goes as follows. You are given two lists of integers, nums and costs. Consider an operation where you can increment or decrement nums I for cost I. Given you can perform any number of these operations and you want to make all elements equal in nums, return the minimum total cost required. Complicated, right? Well, don't worry, we're gonna go through it and explain everything. So, I found out two approaches by studying other people's answers from the contest, and we're gonna go through them. So the first one is binary search. So here we have our nums and the cost. Let's say we want to set all numbers equal to any number x. Well, we can define the cost of setting all numbers to that value by this function here, which is the cost of the value times the absolute value of x minus that number, so basically the distance between them. So what this gives us is the combination of multiple absolute value functions, which we can looks a little bit like this. And when we have a function that has one minimum or one maximum like this, we can do a binary search for that minimum, because we know if the slope at where we are is descending, we have to go left, and if the slope is descending to the right, we have to go right. So we go towards where the slope is descending, which wouldn't work if we would have multiple minimums. So let's say we would have any function, let's say something like you have a hole here, then it goes back up here, and then you have a slope here. So let's say you would be here, you would go in the same direction as the slope, but if you're here, you would go to that direction. So eventually you would converge towards this point when the real minimum is here. So first we have to prove that there is only one minimum to the function of the cost we described, the cost function we described. So let's try to do that. So my approach for proving it is, at first you start with the first function. Let's say in our initial example here, we start with the lowest value nums I, and at that point the slope of every other number is descending because we haven't reached it yet. So it's like if when we were at the minimum of 1 here, when we are at the minimum of 1 here, it means we're like at this point in this function and like here in this function. So every function is descending. Then when we go to the right, this one is gonna start to go up, and the other ones are gonna keep going down until we reach the minimum of the next function. And then at that point, this one is gonna go up. So the effect that has is basically, in the beginning, like every function is going down, and one function at a time, or one number at a time, there's gonna be a small push towards the top. So it's gonna do some kind of curve like this. The more functions start going up, the more the total cost functions is gonna start going up. So we can search for the minimum here. And we can look at the example. It looks a little bit like this, like you see this, the slopes starting going up from here. So let's look at what the code looks like. So here we have our function down here solved by binary search. And it's basically just finding the peak. So to find the peak, first we have to implement the cost function that gives us the cost for a given target. So here we have our cost function, and basically iterates over every number and computes the distance between the target and the number and multiply that by the cost. Okay, so now that we have that, we want to search the minimum between 0 and the maximum of the numbers. So that takes into account that the minimum number can be 0 and there's no negative values, because it's not going to search in that range. That may be a mistake, but let's make that assumption. So now we take the middle value and we look at the slope. To look at the slope, we compare with the value next to it, and if the slope is higher, it means that the slope is going down, and if it's lower, it means that the slope is going up. So if the slope is going up, we want to reduce the higher bound, and if it's going down, we want to reduce the lower bound. And we keep going like that until the two bounds converge to one value, and then we return it. When we're done, we just return that value. So that's the binary search method. Now let's look at the median approach. Okay, so by definition, a median is the value for which the absolute distance between every value is minimized. But that only works without the cost from the problem. So maybe if we found a way to remove the cost completely from our numbers array, then we could just find the median. So actually there's a way to do that. Like, let's consider the 1 here. So every step we move away from the 1, it adds 10 as a cost. So what if instead of having 1 that costs 10, we would have 10 ones? So when we would step one step away from the 1, it will still give us 10 cost, but without the concept of cost. So this is what I did down here. Basically, I put the number of times the number, I repeat the number by the cost of its value. So here there's 1, 2, I put 10 ones and 2 3s. And then if we sort this and find the median, then we will have our value. So that's what I did with the solve math method. So here we zip the number and the cost together, so we can know which number is associated with which cost, and then we sort them because we have to sort our numbers to be able to find the median. And then we iterate over the pairs of numbers and costs. So we find the position of our expected median, and then we reduce it by the cost of the current value. And if it's still within bounds, so let's say the median is still after the value that we reduced by the cost, we keep searching, but if the cost is greater than the median, it means the median is within the cost of that number. So then we must compute the cost for that number and return that value. And if we reach the end, well, the optimal cost is for the last value. Crazy, right? Thank you for watching. See you next time.